Okay, we've got 1:30, so why don't we get started? Good afternoon, Research Methods. Wow, that was a terrific orienting response. Welcome to Wednesday of week number 11. We're going to be finishing today's session by handing out article analysis number 3. This will be due on Friday. I think you'll enjoy it. We took a peek at this last time around. Just wanted to remind everybody that this is what the article looks like. It's from Psychological Science, which is one of our most prestigious and yet most readily accessible kinds of journals. I think you'll find this relatively easy to read and a really interesting topic. And we'll also get the chance to apply some of our skills to this. I think this will be a fun assignment for us. Hope you enjoy it as much as I have over the past couple of semesters. Okay, so that's what we're doing for Friday. And what I thought we'd do is pick up on our conversation from the other day. We were talking about ANOVAs, and we were more or less done with the 11.5 PowerPoint presentation, but these are always some tricky issues for students, and I thought we'd give you the opportunity to warm up on this a little bit before we actually make the computation. Today we'll be doing some computations in Excel, we'll be doing them in SPSS, and I think this will set you up very well for having a deeper understanding for some of the issues that you'll be reading about in the article, and also it will set the stage nicely for the upcoming quizzes that we'll have on computers in the future. Okay? So why don't we go ahead and just remind ourselves a little bit about the one way within Subjects Anova. So let's take that phrase by itself. What does one way mean when we talk about a one-way ANOVA? One way? What is meant by that? You can yell it out. One independent variable. Natalie's got it, right? So we've got one independent variable, and starting next week we're going to introduce 2 independent variables, but for right now we're still at one independent variable. Within subjects, can somebody distinguish what we mean when we say within subjects versus between subjects, how we go about defining that? Who can help us out with that? Okay, we'll go with Jenna, thank you.
Within subjects, participants get all levels of the...
Okay, in the within subjects design, also called a repeated measures design, each participant receives each level of the independent variable, and in a between subjects design we'd have each person receiving just one level of that independent variable. Okay, so that's one way and within. Please go ahead.
Can you repeat that?
Yeah, so in the within subjects design, which is also a repeated measures design, we use those terms interchangeably, each person receives all levels of the independent variable. I should say probably each participant, because person implies human. We frequently run humans, but we also have researchers here in our department who work with non-human species. So each participant receives all levels of the IV. By contrast, if we had a between subject design, you would be receiving just one level of the IV, and we define the IV, or independent variable, as we had from the first week of class, the variable whose effect we seek to know. Okay? All right, so that's a little bit of background there. We had this idea about the ANOVA relying on some assumptions. Somebody want to remind us what the assumption was that underlies the within subject ANOVA? What's that assumption called? Okay, yeah, thanks. There it is. Sphericity, all right, sphericity, right? Let's all say sphericity so we can practice that. Sphericity, okay, yep, it's a motor skill saying that, okay. Anybody want to remind us a little bit about what that's like? It's actually a very complicated mathematical idea, but we can at least have an intuition about it. What is the sphericity assumption? Anybody want to step us through that one? Kip, I think you did it yesterday. Can you?
Yeah, essentially it's just all the correlations between each condition of the variable must be relatively equal.
Okay.
If there are like 3 conditions, 1 and 2 must have a like equal correlation of 2 and 3.
Yeah, okay, right. So the idea would be that we'd have equal correlations across our various conditions. Here's something I didn't mention yesterday, but I really emphasized in the video. What goes on in the sphericity assumption if we have a within subject ANOVA, and we have 2 conditions, condition A and condition B? Anybody want to tell us about the sphericity assumption in that case? We didn't mention that yesterday, but it did come up in the video. Jenna, can you help us out with that?
In that case, it can't be violated, the sphericity assumption, because it's only called in question when there's more than assumptions. So because if there's only two, there's no comparison.
Yeah.
There's no third condition to compare it to. So you can't say like A equals C, B equals B.
Yeah. Right, okay, so if we have just two conditions, and you can run an ANOVA with just two conditions, you wouldn't have to, you could run a t-test in that case, but you could, and then sphericity would be automatically assumed. There would be no violation of sphericity because, as Kip was pointing out, and Jenna is re-emphasizing here, we're usually looking for similarity across correlations. Correlations all automatically require two variables, variable 1, variable 2. So there's going to be a correlation there. And if those are your only two variables, that's the only correlation you have. So that correlation couldn't be different from anything else. Who's following that logic? Does that work for us? Okay. It's a little bit similar to the idea back in the within subject t-test. We actually don't have an equal variance assumption in the within subject t-test. And the reason is we take the two conditions, we difference them, and we're only looking at that one set of scores. And because we're only looking at one set of scores, that will have its own variance, but there's no other set of scores that could be different from it in variance, right? There's only one set of numbers. Here we have, in the within subject ANOVA, only one pair of conditions if we're doing a two-level ANOVA, and so we have sphericity automatically assumed. There was one hand that went up a moment ago. Go ahead, Kip. Thank you.
This is a little bit off topic. I'm just wondering, why is it called the sphericity assumption?
Yeah, right. So actually, there's whenever we're doing algebra, and in part we're doing algebra here, there's almost always a geometric equivalent to all of these. If you take the next course up, I would show you one more time the R statistic that we've computed, and we've done it algebraically here. There's a geometric equivalent to that. And when you're dealing with lots of different matrices, you can think about the properties of those matrices geometrically. And once you're talking about geometry, you can think about spherical kinds of properties, and there are mathematical definitions of those. So it comes from some of the underlying geometry in those complicated matrices. Hope that puts you in the ballpark anyway. But if you wanted to know even more, I could show you pages of graduate text on that. Okay, but great question. Okay, so now we've got the sphericity assumption. People seem to be pretty comfortable with that. And we have this two-step process. Can somebody remind us about the two-step process that we did for the within subject case? It was similar to the one that we had done for the between subject case. Okay, we'll go with Meg.
The first step is whether or not you want to view you keep the sphericity assumption.
Okay, right. Huh?
And the second step is retaining or rejecting
The null hypothesis, which is always about means. Okay, so it's similar to what we've done before. It's a two-step process. We evaluate the assumptions. If the assumptions are okay, then we proceed and we evaluate the equality of means null hypothesis, which is always the null hypothesis when we're doing t-tests, when we're doing ANOVAs. Those are always based on means. Who's okay with all of that? Let's all yell it out. The name of the test that we would use to evaluate sphericity is Mauchly. Shown here. Okay, Mauchly's test. All right. Okay, and so let's just make sure people are okay with it. We did this yesterday, so a little bit of review, but sometimes it's best when we get into the trickier material here if we take 2 steps forward and 1 step back. And so we review just a little bit at the start of each day. So here we're going to wind up retaining or rejecting. What are we doing in this case? We're going to reject because that number is 0.05. That's a rule that never changes in this class, right? That's less than 0.05. We reject something. At this point in our decision tree, we were evaluating the assumption. And because it's a within subject ANOVA, we're evaluating the sphericity assumption, Mauchly's test of sphericity. So we really can't assume sphericity here. So before I go on to the next slide, can somebody tell me what I'll see on the next slide and what I should do on the next slide? Who can help us out with that? Okay, we'll go with, yeah, Mira? Yeah, okay. Yeah, right, okay. So we're going to go to this thing, and we're going to see that we have lots of different sig values, which might seem problematic. The one-liner that we had the other day was, a person with a watch knows what time it is. A person with 2 watches can never be sure. Here we have 4 watches. Which of those 4 do we use? And because sphericity had been violated, we can't assume it anymore. We have to go with one of the corrections. For simplicity, we'll go with the next one down. Okay? If we took another class in stats, we might quibble about which of these would be the better move. There's even an entirely different kind of a move called a multivariate statistic, which would get us out of this problem entirely. But for our class, we'll do a binary decision. If we assume sphericity, top line. If we don't, greenhouse geyser line, line number 2. Okay? So I think we pretty much have that one down. I think that's always a little bit confusing to introduce, but I think with some practice, we get there. Okay? Here's another point I didn't make yesterday, but I'll just see if somebody can help us through this. We didn't yesterday talk about the epsilon values. But I mentioned them in the video, and I wonder if anybody wants to begin to share with us how the epsilon values work within the sphericity adjustment. And we had the Greenhouse-Geyser adjustment. We have some other ones. Here's one called Hohenfeld. Here's another one called lower bound. Lower bound might be easiest to think about because it's a nice round decimal, 0.5. Anybody want to help us with how that went? Okay, thank you, Jenna.
Epsilon values are like coefficients.
Uh-huh.
And in order to kind of to do that relationship, you want to look at the lower bound,
Okay.
which will be your coefficient, and multiply that by your degrees of freedom.
Yeah.
And so that makes it harder to beat the number to beat.
Yeah, right. Very nicely stated. Let's take this number just for a moment. We could have used 0.639. We could have used 0.615. The reason I'm using lower bound here just for the moment is because it's a nice round number, and I bet many of you in your head can multiply things by 0.5 or basically cut that number in half, which is what you're doing when you're multiplying by 0.5. You're cutting something in half. So we'll look at the lower bound adjustment just for a moment, and we'll come down to here. And let's just pretend for a second that we had assumed sphericity. We'd be on the top line, we'd have 2 degrees of freedom, and we'd have that f value, we'd have that sig value. Who's okay with that? Remember that we have to typically report 2 different kinds of degrees of freedom, one for the numerator, one for the denominator. Had we assumed sphericity, our numerator degrees of freedom would be 2, our denominator would be 34. Who's with me so far? Okay, okay, so that's nothing new. But now we throw in this wrinkle of the sphericity assumption. We'll pretend that it was a rejected assumption, and so we have to make some kind of adjustment to it. We're going to go with Greenhouse-Geyser, but for this conversation, we're just going to pretend that we've got the lower bound adjustment instead of Greenhouse-Geyser. Remember that coefficient was what? Can you yell it out? The number from the other page? 0.5, okay? So what we're going to do in this lower bound adjustment is we're going to take the degrees of freedom, 2, and we'll multiply it by 0.5. Can anybody do that in their head? 2 times 0.5? How many people are coming up with 1? Okay. In other words, if you cut 2 in half, you'd be left with 1. Does that work for us? So now we're down to 1 degree of freedom after having made the lower bound adjustment. Who sees where that number came from? Okay. All right. Let's do it here again. We started out with 34 degrees of freedom, 2 and 34. Had we assumed sphericity, had we made a lower bound adjustment, we take that number and multiply it by 0.5. Can anybody cut 34 in half? 17, and that's what we have here. Okay? So then what we might say is, if we're reporting this, we might say, oh, we've made an adjustment. We might have said we made a lower bound adjustment, and we wound up with 1 and 17 degrees of freedom, as opposed to saying that we had 2 and 34 degrees of freedom. Okay? So in other words, what happens is a little bit like playing an American football game where you get assessed a penalty. Right? We're going to, instead of saying you have 34 degrees of freedom to work with, you have only 17 degrees of freedom to work with. And the reason that matters is that tends to adjust this thing. That moves this thing left and right. And as we get fewer and fewer degrees of freedom, this tends to move further and further back, and it gets harder to beat the number to beat. Who's following that? So in other words, if we violate the sphericity assumption, we pay a penalty. We pay a penalty most exquisitely here in the degrees of freedom, but that alters this thing, and that changes our sig value. And it changes our critical value and our sig value. That's how that goes. Of course, if you don't have a sphericity violation, then you get to keep all your degrees of freedom, and you've got the best chance of beating the number to beat, best chance of getting a low sig value. Okay? That's how all of that hangs together. Please.
So when you reject the sphericity assumed, you...
We're going to go with Greenhouse-Geyser. I was using lower bound just as an example, but we'll always stay on Greenhouse-Geyser.
Oh.
Okay?
So the lower bound adjustment is for what?
You don't need to use it. Okay? We could have adjusted, if you violate sphericity, you can make any number of corrections. Okay? You can correct it any number of ways. We're going to go with the Greenhouse-Geyser. The reason, Katie, why I asked you to think about the lower bound adjustment just because it happened to have a coefficient of 0.5, and I knew that you could do that in your head, I didn't think people could as easily multiply 0.639 or 0.615. Okay, so it was just for illustrative purposes. But it also makes the point that you could have gone with lower bound, right? You could have done that, but in our class we're going to go with Greenhouse-Geyser. Please go ahead.
Just to contextualize this, would this kind of table show up in SPSS? Or when would we see something?
Yeah, this is an SPSS printout. So I actually created a problem, I ran it in SPSS, and then I scanned it in. So this actually is the SPSS. And we're going to do one in about 11 minutes. Okay, all right. Something else. So we will see this coming up in just a moment. Okay, let's now go on to our other big feature from yesterday, just as a review, and that's our new friend Bonferroni. Let's all say Bonferroni, everybody? Bonferroni, all right, there you go. Now there's a name, okay? And let's see if we can do this Okay, we had a little bit of practice yesterday, so sorry for the redundancy, but we now run our omnibus F, that's this big F, and it tells us good news, sphericity is cool, and good news, you can reject the null hypothesis, but maybe you have lots and lots of different conditions. You know, we talked about Baskin-Robbins having so many different flavors, right, and we're comparing the flavors to each other. Let's just say we run 5 t-tests. We compare vanilla to Rocky Road, and we compare vanilla to strawberry, and we go through 5 different combinations. One of those t-tests produces a sig value of 0.015. Normally, would we retain or reject given that sig value? We would reject because it's less than 0.05. So nominally, we would be rejecting. Okay? But remember that we're cheating a little bit here. We had 5 chances to win. 5 chances to win that lottery of statistical significance. So we have to make a Bonferroni correction. And somebody pointed out yesterday that we wind up scaling that thing up by a factor of 5 because we ran 5 t-tests in this hypothetical. Okay? So if you want to use Excel, I'll let you use Excel now, or maybe you can do this in your head. The question becomes, would we retain or reject this one, given that we've had 5 t-tests and we're making a Bonferroni correction? Okay? So we'll let you think that through just for a moment, and we'll let you vote with one finger as to say, I want to reject after Bonferroni. 2 fingers means I want to retain after Bonferroni. 3 fingers means I don't know what this guy is talking about. Okay? So we'll let you maybe do that mathematics in your head, or if you want to use Excel, you're welcome to do that. I'll give you just a moment. 1 is reject, 2 is retain, 3 is I don't know what's going on here. Pretty cool. Okay, I'm seeing roughly, for those of you who are voting, I'm seeing a sea of 2s, and that's good news. I wonder if we can go with Brittany. I think you put up a 2. Okay, now we're not so sure why we did a 2. Okay, why don't we go with Katie?
I just multiplied 0.015.
And what'd you get? Okay, so nominally we had 0.015, that would be reject. Katie correctly multiplied by the number of t-tests that we ran. Remember, every time we run a t-test, we get another lottery ticket. If we run only 1, that's cool, but if we run 2, now we've changed our cumulative type 1, so we need to make an adjustment. She correctly multiplied that by that, and you said you got 0.075. The newly adjusted value is 0.075, which is greater than 0.05. Remember our rule that never changes. If it's less than 0.05, we reject. Greater than we retain. So hopefully everybody here had a 2. That work for us? Yep, okay. Let's go on to another one. Okay, we'll let you vote using the same voting scheme. Instead of having 5 tests, we still have the same Baskin-Robbins flavors, but now we run just 4 t-tests. Okay, we'll let you vote. Okay, Lauren, can you tell us, that's correct, you put up a 2. Can you tell us how you got that?
The same way that she got it.
Okay, okay. 4 times 0.015 is? 0.06, so we missed it by that much. We got really close. So if we did have the F value there, and we would be out here. We're actually, if we're running t-tests, we would be almost all the way there, but we wouldn't be over. We'd be at 0.06. We need to be at 0.05. Okay, let's see if we can move this along. Say we've got 3 tests. What do we want to do in this case? Giselle, do you want to help us out? That's a correct response.
We would reject it because the value is 0.045.
Okay, right. So 3 times 15 is 45, and that's going to be 0.045, which is just a little bit less than point. So we just made it. By the hair of our chinny chin chin, we're just on that side now. A moment ago, we were just on this side. Now, finally, we're in on that side. Okay, let's do 2 more. Okay, now what we're going to do is we're running 2 t-tests. Okay, post hoc, which is after the fact, after we've run our omnibus, we now run 2 t-tests, and one of those 2 generates a sig value that's pretty interesting, 0.04. Let's vote with our fingers. 1, 2, or 3 fingers. Okay, I'm seeing 2s. Okay, and why don't we go with Katie B? That's correct. 2 is correct.
The value is 0.08.
Yep. Okay. Right, 0.08. One last one, if you'll bear with me, okay, just so that people get to really practice this. We have 2 t-tests, and we come up with a 0.015 on chocolate versus strawberry. Okay, go ahead, Kip. All right, so that's how we do that. It's that simple, okay? But what we've done is we've made a very, I think, intuitive kind of correction for this cumulative type 1 error. The other reason why we got into this really is because SPS itself doesn't do this automatically. Interestingly, the programmers there made a decision not to offer us any kind of post hoc adjustment in the within subject world, but they do so in the between subject world. So that's how we got here. All right, any questions on any of that? I think we've got the conceptual stuff down. And now what we might try to do is go off to maybe Excel, and we'll see if we can do some of these problems with a within subject ANOVA using the basic ratios. And while we're getting set to do that, if you could pull out this one from 1 or 2 days ago, this is the handout that we had. It shows our basic ratios. And we introduced a brand new basic ratio just yesterday. Does anybody remember what the new basic ratio was out of these 4? S. And what does S do for us conceptually? All of these things get us sums of squares. Anybody remember what S helped us do?
Decrease the error in the denominator.
Perfect. It decreases the error in the denominator. You might even notice that there's a minus S down here on the other side in the denominator. And specifically, we're decreasing it by the consistent individual differences. And that was our motivation for doing these. So if you would join me by going out to the practice problems. And in the practice problems, there's a subfolder called One-Way ANOVA. And then there's ANOVA basic ratios, and that's what we're going to do here. We'll get some practice computing those. And we did, at this time last week, we did the between subject family, where we learned about the basic ratios y, a, and t. We're going to do that one more time now in the within subject family, but we have to introduce this new basic ratio s so that we can remove from the denominator the consistent individual differences, the fact that Pedroia is a better hitter than I am, regardless of what color that baseball might be. Okay? So here we are. It's something like that. And I'm going to amp this up just a little bit for our folks in the back.
Wait, what is this up there?
This is, okay, it's going to be called Within One-Way ANOVA Basic Ratios. It's going to be pathwise. Out on RS drive, 203. We're going to go to practice problems. One-Way ANOVA problems. And then it's in this one, ANOVA Basic Ratios. And it's called Within. So we'll make sure everybody gets there. Maybe you can see the path up that way. Practice problems, One-Way ANOVA problems, and then ANOVA basic ratios. It's the one that's labeled within. And by show of hands, who's been able to find that? Okay, I think everybody got it? Yeah, okay, good. All right, so here we are, and we're even going to hand you our null and alternate hypotheses, which are in the population all means are equal. This is a very simple one. We have 3 conditions. We have 4 participants. So we can think of this as white, red, and green baseballs, if we want to think of it that way. And we're tracking something like the number of hits. Okay? And so if you've got this in front of you, we're going to be plugging first on this page. And we need to get a couple of rudimentary quantities first. We always start out with sums. And we did this last time. So if you'll join me by clicking right under here, and we'll call this a sum. And we'll take the sum of column 1. And I come up with 104. And then once we have that spatial relationship, we can drag that over. And then I come up with 70 and 84 as my sums. For the 3 different conditions, we'll call them, white, red, and green baseballs or something like that. Okay? How many people can confirm those numbers? Okay, that's really easy. The new wrinkle now, this is what we used to do in the between subjects case. We're doing that again here because we still need to understand the between condition variability. We also need to know the consistent individual differences. So we're going to go next to the C3, we'll put in sums, and now we'll get the sums for the different individuals that we have. This will be equal to the sum of participant number 1's 3 scores. They had a score in condition 1, 2, and 3, the white, red, and green baseballs. And we can drag that down. And you don't have to do this, but I'm going to make the bottom right corner the grand total. I'll put it in red. Okay, so I built it once. That was simply the sum of C1, C2, and C3 for participant 1. I dragged that down, and I have all of this. These are now raw scores. Show of hands, who has that? Okay, and that should add up to 258, and those numbers again were 88, 82, 36, and 52 as the sums for these 4 different folks. So you can see somebody's really a better hitter than somebody else. Looks like participant 1's got 88 hits, and participant 3 has 36 hits. Please go ahead, Jen.
Why does it have those green
Yeah, I'm not entirely sure why those things pop up. There's something about internal referencing inside of Excel where if somewhere in this long list I'm referring to that cell somewhere else, then it pops up as green, I've noticed, okay? But it doesn't tell you that anything's funny there, okay? Sorry that I don't have a more detailed answer than that. Okay, if you'll join me by doing this, we'll just remind ourselves that these are raw scores, okay? So that first matrix, this sequence of rows and columns, we'll call it a matrix, is for the raw scores. That's maybe the number of hits that these folks are getting. Anybody want to remind us what we generally do after we have our raw scores? We did this once or twice before. Marin's got it. We're going to do our squared scores. So if you'll join me by highlighting over anything that you want, like maybe that big, we can now do Control-C, Control-V, and we get a duplicate, which all by itself would be pretty uninteresting. But we can take advantage of some of the structure here, and we can change the word raw score to squared scores. We can also highlight over the numbers in that group and get rid of the raw scores. And now simply make sure that every cell here is a squared version of its counterpart upstairs in the raw scores. So I'll start out with C1. This will be equal to C1 up there in the raw scores squared, and I come to a 1444. I can drag that down, I can drag that over, and I'll make that red. Okay? And now this is a squared that. Okay, that's all that we have. In third grade, when I was growing up in New Jersey, we used to think this was hilarious. We used to say, you know what this is? This is a dead that. Okay? We got a big kick out of that in third grade. This is a squared that. That's all that is. Okay? How many people can confirm 66, 564 in that lower right corner? Okay? So we're not going to take the sums again, we're just squaring each of those sums. Now what we're going to do is start working our way toward the basic ratios. We used to have 3, and now there are 4. Heads up, next week there's going to be more than 4, so we're building on these. You'll see these perhaps, but some other ones as well as we add a second independent variable. Okay? But we're just building it up one step at a time. Now we're going to go with our basic ratios. And we'll call them in our order Y, A, S, and T. So the basic ratio Y has its own computation here, which I promise you will not have to memorize. I will hand this to you the next time we have a computer quiz. I haven't memorized these either. Okay? And what we're going to get here is the sum of the individual squared scores. Just for clarity, I'm going to highlight those so people can see where those are. These are the individual squared scores, the ones outside of the yellow region were some kind of row totals or column totals. So we'll say equals sum, and we'll go over those. And I wind up with a 6378. Can I get an amen on that? Okay, all right, that worked. Did anybody not come up with 6378? It's okay if you didn't. We'll have your neighbor help you out. Okay, so we want to highlight over those yellow items, all of which are simply squared versions of their counterparts upstairs. Okay? Now what we want to do is get some indication of the variability that we have across these different conditions. These were different baseball colored conditions. So we'll say equals, and we'll take the sum of the squared column totals. Just for clarity, I'm going to make them a different color. You don't have to do this. But these are now the ones that are shown in blue. So equals the sum of those 3 blue column totals divided by the number of conditions that we have. Can somebody yell out the number of conditions? 3? Okay, do we see where that number came from? Oops, excuse me. Sum of that divided by the number of, I'm sorry, the number of subjects. I'm reading the wrong line. I apologize. The number of subjects. How many subjects do we have? 4. Okay, right. 5693 is where we should be. So it's number of columns divided by the number of rows. And we're going to flip that around in just a moment. Who can confirm 5693? Did I lose anybody there? Okay, thank you. Okay, so what we're doing here, Brittany, is we're taking basic ratio A. And as you can see, it's the sum of the squared column totals divided by the number of subjects. The squared column totals are shown here in blue. So we'll take those sums. And then we'll divide that by 1, 2, 3, 4 subjects. Okay. Does that make sense for you, Brittany? Okay, great. Now we're going to do almost the reverse of that. We're going to get the quantity S, the sum of the squared row totals, divided by the number of columns, which is to say the number of conditions. Okay, so we'll say equals sum. And we'll highlight over these guys, which are starting at the 77 number, ending with the 27 number. We'll take that sum, and we will divide that by the number of conditions. And we said a moment ago we have 3 conditions, and that gives us a 6156. Who can confirm that number? Okay, and we'll pause because I think one person is not quite with us. Are we okay?
No, mine's not like working. I copied and pasted it, and now it's like I'm trying to square all of them, and they're not squaring with like the same numbers.
Okay, so did you click on the 38 and square that and get 1444?
Yeah, no, I got all of those, like the ones for subjects, but the sums are not.
Okay, and then that number is only 104 squared, right? It's not the sum, it's 104 squared. Okay, all right, so if we square the 104, we come to the 10,816. Okay. All right, and let's now go on to a mistake that I'm going to make here. I'm going to deliberately make a mistake for everybody to see because one of you will make this mistake soon enough, and I wanted to exhibit this mistake for you. We're going to get a mistake on the final quantity t here. Actually, we'll do that mistake in just a moment. But I wanted to flag you that we're going to give you a mistake and then correct that for you. For the moment, let's just go with t equals this grand total squared, which is the 66,564, divided by a times n. Can anybody do a times n in their head? 12, okay, right, because we have a conditions, which would be 3, and n is 4, so 3 times 4 is 12. We'll divide that by 12. If you wanted to spell that out and do parenthetically 3 times 4, that's fine as well. And we come up with 5547. Who can confirm that number? Okay? All right, so we're just about there. Rachel, is that working for you? Okay?
I got lost at S.
Okay, let's go back to S, okay? And so what we're doing here, I'll turn these guys green, so those are really obvious. What we're doing here is we're taking the sum of these row totals, okay? And then we're dividing that sum by the number of participants that we have. Oh, sorry, by the number of conditions that we have, which is 3. So it's that number divided by 3. In one case, we're doing summing over the columns dividing by rows, and then we do the inverse of that. We sum over the rows divided by the number of columns. Okay? T was equal to this guy on the bottom. Yep, that 66,564 divided by a times n, which people were telling us is 12. Okay? Because we have 4 participants and 3 conditions. 4 times 3 is 12. Please go ahead.
So the only thing that we have to memorize for this one is like the raw, like doing the sums and the squares.
Just this procedure, right? So you'll have this in front of you, but you want to make sure that you know how to take the squares appropriately and lay it all out. But you won't have to memorize the formula. Okay? All right, let's go ahead then and begin right underneath these numbers. Remember that basic ratios help us get sums of squares. Who remembers that? I mean, that was our mantra. So let's get some sums of squares. Next to the sums of squares in our F table, does anybody remember what came next? Yell it out if you know. I think I hear it. Degrees of freedom come next. Okay, then what happens to the right of the degrees of freedom? Okay, the mean square, which is also the variance. Okay. And in an analysis of variance, we analyze variances or mean squares, and we wind up with an F statistic. Okay, so those are most of the columns. Sometimes we say over here that we have a source of these errors, and generally we have some kind of between condition source and some kind of within condition source. But what we're going to do this time is something just a little bit different. We're going to put this down by 1, and we're going to leave a space for the subject component. Jenna reminded us earlier that we're going to pull out from the denominator this S bit, so we'll get a subject component here. Okay? And we'll begin filling out this F table, and we might even go further than that. Okay? Okay, so let's begin by looking at now this side of our handout. Okay? And this tells us how we mix and match these basic ratios in order to derive our sums of squares. So we're looking now not at this side, but at that side. And we get these little formulas, again, that you don't have to memorize. And if we're looking at the between conditions, we can see that the sums of squares comes about through what? I'll let you yell it out. Equals a minus t. So let's do equals a minus t. Okay? And here we're allowed to breathe a sigh of relief. And why can we breathe a sigh of relief? Anybody want to remind us? That may or may not be the correct number, but at least we know it's not negative. Okay? Had this been negative, we know that we would have made some kind of an error for sure. And every year I typically get 1 or 2 students that wind up with negative sums of squares on a computer quiz. So that at least passes a smell test, so to speak. Okay? Let's go now to the subject line, and we'll do equals s minus t. Whew. Okay, that one is also a positive sums of squares, so that's pretty good. Okay, let's go to our within line, and here a moment ago I promised you that I'd make an error, and I'd like you to see the error that I'm going to make. Sometimes we get a little ahead of ourselves and we see all of these letters here on the bottom line. We see Y, A, S, and T, beautifully aligned here. We see some negative signs, and we tend to do this. Equals Y minus A minus S minus T. Uh-oh. What did I do? Go ahead, Kip. I subtracted t instead of added it. So notice that 2 of those are minus signs and 1 of those are plus signs. I know that you're seeing that right now, but when you're a little bit anxious and you're in the middle of a quiz and that clock is ticking away, we want you to be very comfortable in just remembering that there's a positive sign in front of one of those. So if I leave that computation, but now I change that last minus sign to a positive sign, now I'm back to a positive number 76. Who's okay with that? Okay, all right, let's go ahead and move through our degrees of freedom. This is going to be lowercase a minus 1, which is going to be 3 minus 1 or 2. Okay. I can also do the n minus 1 for the subject's degrees of freedom. And there were 4 subjects, minus 1 will give me 3. And then I can do the product of those two. This is a minus 1, that's n minus 1, so I can now complete that. This times that. Okay, and I wind up with 6. Show of hands, who can confirm 6 degrees of freedom? Okay, that working for us? Now we'll go ahead for our mean square. Okay, and now what we're doing is we're using the mean square for this between as being 146 divided by 2. Okay, and then we can actually drag that all the way down. And we have all different kinds of variances. And then finally our F ratio for the between conditions factor is going to be this divided by its error term, the within subject term. If you prefer, we can call this error. And we wind up with an F statistic of 5.76. Hang on. Oh, sorry. Sure. Let's do that again. I think I lost a couple of folks there. Let me go back to here. Who is okay with my getting the mean square? Does that work? Okay. I got the mean square, which is always SS divided by DF. So it's my neighbor 2 doors to the left divided by my neighbor immediately to the left. I'll do that again. Him divided by him, and I get that. Once I have that, I can drag that down. And I get all of these different mean squares. It's always my neighbor 2 doors to the left divided by my neighbor to the left, SS over DF. Okay, does that work for us? Now what we've done is we've essentially taken this error term, which used to have all of this variability inside of it. We sucked that variability out, and we were left with a much smaller error term. Now we divide 73 by 12.667. Okay, to get to our F ratio equals that divided by that. And we wind up with a 5.7632. And we'll see how many folks are with us still. And we'll see if we lost somebody. It's okay if we lost you? Okay, Nina, thank you.
No,
You're there? Are you okay? Okay, everybody, how are we doing?
there, I just don't really understand.
Okay, good. Okay, let's take a moment. So what's new here, thank you for the question, Rachel. What's new here is what I'm going to put into a new color. Why don't we go with that light blue color? Okay. So what we did in this line and that line we've done before. Today what we're doing, something new, and Jenna gave us the heads up about this, is we had to, in the within subject case, remove consistent individual differences. In order to do that, we had to compute this guy for the first time. That was some way of quantifying just how much better Pedroia is than I am as a hitter. Okay? But now we have to do that over 3 conditions, which is a little bit messier than doing it over the 2 conditions that we had yesterday. So this stuff used to be jammed down here. That gave us a really, really fat denominator. And when we have fat denominators, our F ratio gets to be really small. But we can improve the sensitivity of our test by pulling that out because it's not relevant to our question about which ball color is most easily hit. And now we wind up with a 5.76. And that's going to put us, somewhere out here. We don't know how far. Maybe we're past that line, but we're way past 1 anyway. Did that help? Yeah? Okay, great. Thank you for the question. How are we doing? How many people are ready to go on from there? Okay, why don't we do it this way? Why don't we just see what the sig value would be for this? That's the p-value. We can also call it the sig inside of SPSS. Okay? And you tell me, you yell out the command that we would need to get the sig value or the observed alpha level. Those are fdist. So we're going to say equals fdist. Okay, this might be just a tad confusing. I wish the Excel programmers would have given us an f there, because they're asking us to put in the observed value of f, which is right next door. But they give us an x instead of an f. Shame on them. Okay? All right, degrees of freedom. Can somebody yell out what numbers we should put in here and why? 2 and 6. Did that work for us? Okay, so it's that factor that we're looking at, and that got divided by this number, so the relevant degrees of freedom were 2 and 6. I'll click on that one, comma that one. Okay. And I wind up with a sig value of 0.04. Can we yell out retain or reject? Reject, okay, right? So that means somehow we got to a f value that was bigger than 0, bigger than 1, and it's out here somewhere, and we know we made it past our boundary because we're in the rejection region. We made it past the 0.05 yard line, and we're now on the 0.0401 yard line, okay? All right, all right. Let's go on one more. Let's just see what the f_crick value might have been. We wouldn't really need it. It's going to be redundant, but just in case we want it. Can somebody yell out this command? Equals finv. So if we wanted to know how big our f value actually had to be, our favorite probability, 0.05. We said our degrees of freedom were 2 and 6. Okay, so and I'm sorry that got smaller somehow. I'll make that bigger. So we needed to get to an f value of 5.1. We started at 0. We needed to get out to 5.1. And we got to 5.1 and just a hair more, putting us just under 0.05 at 0.04. Okay? So we're going to wind up rejecting HO. One heads up on today's homework assignment, or the one that I'll hand out that's due on Friday. Well, I'll ask you to be drawing these things, right? And I might ask you to write in a critical value. So you'd have all of this information, it goes from 0 to positive infinity, or negative infinity to positive infinity. Probabilities, t-stats for this nice Gaussian, right? This skewed one is going to be the shape that we have for the f-stat and also for the chi-square. And we could ask you to draw in maybe an f_crick value. So if we wanted to, that particular line, given that we have degrees of freedom equaling 2 and 6. So for any ANOVA that had 2 and 6 degrees of freedom, we need to get out to 5.143. Okay? And we did get out that far, but not by a whole lot, but we got there. Okay? So we've been drawing these almost every day for about a week now. Okay? Anybody confused about any of those pictures? We're actually running an f-test, so we're down on this one. Okay. Yesterday we did the t-stat, so we were up on this one. Okay. All right. So good pause there. I think the whole gang is with us. We'll let you jot down what you want about that. We'll also take a couple of questions or comments. So it does turn out to be the case that at least one of these means is different from another. So we've basically run the omnibus here, and we found out what our sig value is. It's less than 0.05. We can reject. Right? If we wanted to, we could add an APA-style statement. Why don't we do that? Just for practice. So we want to report to our audience, it might be an audience to whom we are writing, that we ran a statistical test that was the f-test, and we had how many degrees of freedom? 2,6 in this case. And the observed value of f was, you yell it out, 5.76, and we might go to 3 digits. I'm not a real stickler on that. Okay? And we can actually report to our viewer, not only was the p-value less than 0.05, but we have it precisely. We know that it was specifically p-value equal 0.0401. Okay? And then we might say, although you wouldn't typically have to, but we might say here reject HO. Okay, so now we've told them what kind of stat, which specific variety in terms of degrees of freedom, what we observed, and yeah, we're rejecting HO. We might be doing that in error. We might be rejecting an error, but if we are making an error, the probability that we are making that in error is 0.04. Okay? So we'd get a f value that large or larger 4 times out of 100 just by chance. Okay? Who's okay with that? We'll now ask for positive reporting. We'll see how many hands we get in the air. People okay with that? I think all hands are in the air. All right. I'd like to play around with this just for a little bit. Can I ask you to dial back up top? We won't go through all the computations again, but I'm now going to put in light gray all of these scores. Maybe I need one shade darker of gray, something like that. Okay, those were all the raw scores. Maybe the number of hits that people were getting on this batting test that we have from Spalding. Okay? What I'm going to do, just for fun, is I'm going to try to find the minimum score. And I'm going to try to find the maximum score. This isn't about hypothesis testing. We're just going to develop some intuitions here. Okay? So I've got a min and a max. Does anybody know, because I know some of you have used Excel before, what the command is for finding a minimum inside of Excel? Equals min. Okay, so I'm going to say equals min. And I'm going to highlight over my gray area. These are all the raw scores. And you might have been able to find the minimum just by eyeballing it. But if you have a really big set of numbers, it can be helpful to have Excel do the work for you. All right, so I'm going to highlight over that. And we get a minimum. Equivalently, we can say equals max. And we can highlight over this. Okay, and I'll make that big. And so we had our scores range between 9 hits and 38 hits in this particular set of data. Who's okay with that? Okay, so it's not a way of describing the data set. The reason I wanted to do that was I now want to play around with some random numbers and develop a little bit further for you something that we did yesterday. We put in some random numbers and we were generating these t-values that were bouncing sort of all around here. And most of them were non-significant, but occasionally we'd get a big t-value that we could reject. Okay, so we'll do that now with the F statistic. So what we're going to do is take this data set that we have and convert it into some kind of random number. Does anybody remember the random number command that we used yesterday? Equals rand between. So can we click on the 38 and let's all go equals rand between. And we're going to try to make this, if you will, empirically plausible. We just ran a hypothetical study and we had something like hits ranging from on the low end 9 to on the high end 38. So why don't we pretend that we're going to simulate that hitting range by putting in numbers that can be as low as 9 and as high as 38. Okay? So equals rand between 9, 38. If I hit the enter key, I get a random number that'll be different from yours. And if I press the F9 key, I get a different random number every time. Who's okay with that? Okay? So what we did was we just randomized one of those numbers, but we kept it in range. Okay? Then we did this. We pulled this down and over. So now all 12 of these numbers are going to be random. Okay? And if you dial down with me, you'll notice that we have all different kinds of sig values going on here. Most of the sig values that you'll see under where it says p sig will be greater than 0.05. But every once in a while, if you press long enough, you'll get one that falls beneath 0.05. But generally, they're quite a bit higher. And you'll notice that sometimes you'll have to go for maybe 20 hits before you get your sig value less than 0.05. Who's all right with that? Okay? So it gives you some appreciation for that. Yeah, I think I've got a moment to do this. I won't ask you to code this, but I think you might find this interesting. What I'm going to do is have Excel take a look at that number and put out reject HO anytime that number falls less than 0.05. You don't have to do this with me, but there's a really cool syntax for Excel. Equals if that value is less than 0.05, then we'll say reject HO. Otherwise, we say nothing. Okay? And then if I hold down this key, and I'll turn that one bright red, you'll see a reject HO only every so often. Okay? And that gives you some idea about how rarely we're actually rejecting the null hypothesis. Who's following that logic? So we're doing like hundreds of these things all at one time using the computational structure that you just completed with basic ratios. Okay? That's how unusual that is. Okay. So we have just a moment or two left. I'll start to hand this out, but I just thought I'd ask any questions on any of this. Great. Okay, that's looking really good. Again, this is available to you out on Blackboard. It's available on the S drive. It's the psychological science report that I think you'll find really interesting. If you'll take one down and pass it, that would be great. There is going to be a point where we ask you to take advantage of those distributions on the board, so you might want to make a note of those so you have the format. And I think everything else will be pretty self-explanatory. Okay, when we come back on Friday, we'll talk a little bit about that article. I've got some extras here in case anybody didn't get anything. Oh, one short, I apologize. Can we pass this down to Mira? All right, great. All right, so we'll talk about that article on Friday. We'll do some more of this work inside of SPSS, and we'll even take a look at some of your reaction time data from last Friday. Okay? Thanks for a great session, and have a good day.
Thank you.
Okay, thank you. See you next time.